We introduce LACT, multi-exposure correction method from under or overexposure image. The proposed task aims to restore an image with appropriate luminance values from an underexposure, overexposure image using the proposed algorithm. Let's see an example of an underexposure image and an overexposure image. First, the luminance-compare module compares the luminance-order relationship between the two images. Then, the overall image features are extracted through a backbone network and a set of transforms are derived through an attention operation between luminance features. A set of transform functions are used to generate a multi-channel representation, which directly applies a color transformation of the input image to create a multi-channel image. Finally, the multi-channel representation is trained through the fusion and post-processing modules to obtain a reliable correction image. This figure illustrates the overall architecture of LACT. In the training process, we take two randomly selected pairs of images as input. The backbone network encodes the input image into image features. The luminance comparison module takes early features of the backbone and extracts luminance features to exploit the exposure conditions of the input image. The luminance-aware color transform combines the luminance features and the image features to estimate the set of transformation functions for each color channel. It then performs a multi-channel color transformation based on the transformation function to correct the exposure of the input image. The convolutional layer then generates a corrected image to measure the auxiliary loss function. Finally, the post-processing module further enhances the image to yield visually pleasing results. The following figure shows the detailed structure of the luminance-aware color transform. Luminance-aware attention consists of multi-head cross-attention, multi-head self-attention, and MLP. Multi-head cross-attention takes image features extracted from the backbone module as query and luminance features extracted from the luminance comparison module as key and value as input. The features that went through the skip connection and normalization process are input to multi-head self-attention, and after the computation is finished, skip connection and normalization are performed as before. Finally, it passes through an MLP layer consisting of multiple fully connected layers to enrich the features. As a result of our luminance-aware attention, we get a set of transform functions. A series of transform functions are then applied to the input image to create a multi-channel representation. The following loss functions were used to train the model. To learn luminance information of the two images, a binary cross-entropy loss function was used as the luminance relationship loss. This loss is used to guide the predicted luminance order relationship to the correct order relationship. Here, the correct order relationship compares the luminance of the two images and sets it to 1 if the input image is brighter than the other image, and 0 otherwise. The way to determine the brightness of an image is to convert the image to a grayscale image using the following formula, which determines the brightness as the average of all image pixels. To emphasize image structural features, we use the perceptual loss, which calculates the feature error between the prediction and ground truth using a pre-trained feature extraction network. This formula uses a frequency loss based on exposure compensation loss and the L1 loss between the prediction and the ground truth. Both losses measure losses in independent domains of the predicted image and take into account what is needed for restoration. We perform extensive experiments to evaluate LACT compared with previous methods. For evaluation of the proposed multi-exposure image error correction network, we use two representative multi-exposure datasets, ME and SICE. The ME dataset consists of multi-exposure scenes, where each scene contains 5 exposure-level images and their 1 ground truth image. ME is decomposed into 3,535 and 1,181 scenes for training and test sets, respectively. We use the training scenes for training the proposed network and the test scenes for evaluation. The SICE dataset contains 589 scenes with various exposures and corresponding ground truth. This chart compares the proposed LACT with state-of-the-art algorithms for multiple exposure correction, FECnet, DBRNENC, SIDENC, CMEC, MSEC. LACT significantly outperforms existing methods on all evaluation metrics in the dataset. We also qualitatively compared LACT with other multi-exposure correction algorithms on the ME dataset. We can see that most multiple exposure algorithms lack exposure information, while LACT has luminance information that is close to the correct image by applying the appropriate exposure values. This chart compares the proposed LACT with state-of-the-art algorithms for exposure correction, FECnet, DBRNENC, RCTN, GenLEN. LACT significantly outperforms existing methods on all evaluation metrics in SICE dataset. We also qualitatively compared LACT with other multi-exposure correction algorithms on the SICE dataset. We can see that most multiple exposure algorithms lack exposure information, while LACT has luminance information that is close to the correct image by applying the appropriate exposure values.